Hello, I'm Eva Ratz. I work at the University Széchenyi István in Győr, and my talk was about air pollution and visualizing air pollution data.
Ladies and gentlemen, it is my pleasure and honor to be here now. And this is a small part of a huge project. I don't want to tell you all the whole story. I just focus here on the air pollution data, our field measurement, and how we could visualize our data using Mathematica. This is a joint work. János Karsai is the person who was awarded yesterday, so congratulations again. And Zoltán Horváth is the leader of the modeling team in that project. Before I start technical mathematical details, I would like to talk a little bit about air pollution. So, why do we still dealing with air pollution? It is a huge and current problem still, not just worldwide and somewhere at the other corners of the world where fast industrial development is still going, but also in middle of Europe, in Hungary and also in Germany, we have problems. So there are some guidelines written by the WHO's air quality guidelines about many components of the air, and unfortunately we are far from this requirement. Even we cannot fulfill the European community's restrictions on air quality. Most of bigger European cities, we have monitoring sites and we are checking air condition more than a decade ago. So we have quite a lot of data, and we can say that we still have problems. And the main cause, although we push down the pollution originates from industrial levels, and we had made really good improvement in some kind of pollutions like SO2, but we have still huge traffic. And as we can see in case of nitrogen oxides, the road transport is responsible more than 50% of the pollution. And also, and then there's another statistical data that 97% of the urban population is exposed to higher ozone concentration than the written in the WHO's guidelines. So we still have the air pollution problem. Or you can see more in European Environmental Agency's report. Now it is available at the last year's one too, at their homepage. So what are we dealing with? So as I mentioned, this is a huge project. We have it's called smart transportation. This is kind of the smart city concept, that if we could optimize traffic so that we can save not only money and time for the citizens, but we could reduce air pollution by a clever arrangement of traffic. So that's why we have a traffic simulation and also a diffusion model system. And they are connected somehow with each other. And we use traffic data and also meteorological parameters and three-dimensional representation of city of Győr. So, of course, we don't have more cities in 3D, but there is another team, mainly from informatics PhD students, who constructed our city 3D CAD representation we use. So how air pollution works. So we have a first emission. For emission, we mean what comes out from the chimneys, from the vehicles, the combustion engines. And then came transmission. Transmission is a very complex and also chemical process. The pollution travels and it reacts with other components of the air, and at the end we get emission. This is what we can measure by our devices. The main problem, the first problem is we have too many data, and the second is we have not enough data, of course, but we have huge amount of temporal data. We have containers like this. In Hungary, we have usually 1 or 2 monitoring sites per city, or for bigger cities. For Budapest, we have 8. They measure, we can consider it continuously, so 5 minutes average data from many air pollutant components, and also meteorological data such as direction of the wind and speed of the wind, temperature, humidity, air pressure, and also solar radiation. But one single monitoring site, or even 2, is far from spatial data. So if we want to do spatial simulation in real 3-dimensional modeling space, we need much more detailed spatial resolution. That's why we started to plan, and we did really some field measurements. Before to plan the field measurement, first we had to look at the data we have, the temporal data. So here is a small slice of our data set. Usually we have huge Excel files with this container data, and one Excel file contains for 1 year data. So we just get it some slice from it and to an Excel file, and now we can import it, and also we do some more cleaning, and we can then have a look at it. So we can see now about, so let's see from the beginning, and we can see about 1 month. Yeah, so we can investigate monthly pattern, and if we go through, and so if we play with it a lot, we will see that there are different seasonal differences. Of course, there's a quite remarkable difference between heating season and non-heating season, because not only the traffic is the source of nitrogen oxides in the air. So if we look a little bit closer, we can see, right, it's well, we're not good. We could see also a weekly pattern and also daily pattern. I'm not sure, it's a little bit slow. But if we, so I will show you later a smaller data set. So normally, it's just like the traffic has a daily pattern, a daily profile. Also, air pollution has a daily profile. We have a huge and morning peak when everyone goes to school and goes to work, and there is a little bit steeper afternoon peak, so it's a little bit longer and not so high. And we can see difference between work days and weekends. And also in Hungary, usually we have a difference between Saturday and Sunday, because at Sunday afternoon we have also a huge peak, because everybody goes, a huge percent of the population lives at the weekend in another town and goes back to work town at the end of the weekend. So, again, it cannot handle, and the beginning of the interval is later than the end of the interval. So, if we, so we can see here the weekly pattern a little bit. So there is a so-called interactive date list plot function made by Mike Hennig-Wrench. It is available in his blog site or website or something like that. And here we have a nice, yes, we have a nice window, but it is slow in this computer, so we can change a little bit more nicely the window of the data. So we can smooth a little bit on the data by using moving average. We can have now a little smaller data. So here you can see the weekend. Yes, it's a typical weekend pattern. So and we can make a huge. So there are missing data, but it can handle nicely, so it is no problem. So sometimes containers shut down and reboot and make some apps again. It starts again later than it finished, so I can pick it back, so it's work again. So here we have moving average, say, just a lot. So that's all. So as we know the differences, so we could figure out what would be the ideal average day. It is out of heating season, and it is not in the middle of the summer, and it should be work day, a school day, not the first day of the week, and so on. So we selected days in September, and we started to work on the place where to do it. We performed two types of, we were thinking about two scales. One scale was a smallest scale is one section of the street or just one crossing. So it's called canyoning. Canyoning is a hot topic in air pollution science now. What is it about? So if we have a street which is narrow enough and there are huge, high elevated buildings surrounding it, it behaves like a canyon. We can observe different fluid dynamics depending on the angle of the wind direction and the building's direction and the canyon's direction. If the wind is almost proportional to the canyon, we can have a passage flow. If it is almost perpendicular to the canyon, we have street eddies. And when it is somewhere between, we can have both at the same time. Of course, if we go to the field in a real crossing, the wind will not keep just one direction, it will move. So we can have both passage flow and street eddies. So then we choose a nice crossing in there. This is a city between Budapest and Vienna, and it has 130 inhabitants, so it's a middle-sized industrial city in Hungary. So we choose a crossing. This is a nearly north, south, and west-east direction. Jókai Street, it's in Hungarian, sorry. If you go to the street, it is also written in Hungarian, so it is useful to learn. So here we have a one-way street, so buses comes from this, a lot of buses come from this street because the city center is up there. And this was the main street between Vienna and Budapest before the ring was built around there. So it is still, it still has a remarkable traffic. So it is quite nice, and I also tell you a secret that there were no plans. So if you are familiar with air pollution science, it is if you have plants and trees, so it makes everything up. So it is hard to follow how the air moves in the canyon. So it's better not to have at first any. And we had air sampling points with the red P something numbers. They are coupled because we used true elevations, 1.5 meters and 3 meters. And we counted traffic manually, of course, with a lot of students involved, and also measure noise. They are the green Zs are the noise measurement points. So here we have there. So if you haven't familiar with it, so it's a little small. And let's zoom in. Okay. So then we choose 3 main roads of there. One of them is Szent István Street, what I have mentioned. It is a main road. And 2 others, a little bit south from it, Szigeti Attila and Fehérvári Street. We choose them because there are the 2 containers. We have one is here, this corner, and the other is on the Szent István Street. So we could use them as control points. But in this case, we used only one elevation, 1.5 meter. How can we sample air? So the problem, these containers cannot be moved. So they had just to put it somewhere. And the gas analyzer needs very restricted environmental conditions, so you just cannot walk to the street with it. So that's why we have to move the air into the laboratory. So we use the sample bags, they're called Stadler bags. This is something like Teflon, so it is just a nylon bag, but it's a little bit harder and better. So it can guarantee that no air will escape. And we had pumps and this wooden skeleton, which ensure with some tubes to get the air from 3 meters high and 1.5 meter elevation. And then we moved the bags to the laboratory and used gas analyzers based on chemiluminescent method to measure NOx concentration and nitrogen oxides together. So let's see what are our results. So here we have this, we could succeed to catch the morning peak and some from the afternoon peak. So these are, we can compare sampling points. This is the crossing data. This is very interesting that there are some huge differences between places. So even inside one crossing, we can have remarkable differences. So there are some peaks, and also there is some place where we don't have such a morning peak. So we can project to the real geometry our results. So this is the average. Just going to make it a little bit bigger. Yeah. So this is the average nitrogen oxide pollution in that point. The point is exactly at the middle of the sphere. This is generated by sphere. And we can see that here we have a polluted corner, and here we have, unfortunately, here we have a high school at this corner. The other corner, we have the National Tax Office. So it's good to know, never go to the tax office. This is very unhealthy for you. So avoid it to go there. We can analyze it step by step for each. So it is early in the morning. Then we have the morning peaks. It's extremely dangerous to go to the tax office in the morning. And at night, of course, it would be good, but no one's there at the time. If you don't like these snowmen, you can change them to boxes. So this is another solution by bubble chart, 3D. The other was sphere. It's going to show. So so this was the crossing experiment, and here we have the main road. So again, we can show the containers. Yes. So it's a little bit. So we can distinguish easily the container data from our sampling data, because we had only 6 times data a day, and the containers have, now I used here for quarter hour time data. So here we also have some sampling points, and the daily profile of each sampling point can be investigated. This is a typical huge morning peak and the afternoon. So it's almost everywhere, we can see. And this is the data of the 2 containers. The other one is at the Szentistván Street, and the other 2 near the crossing of the other 2 main roads we were investigated. So this is a projection again, and this is the real distance between the sampling points. And these are measurements, the daily profiles, and that one is the container data. So I try to move it right straight back, so we can see that the morning peak is almost everywhere the same, but in the afternoon we have remarkable differences, and it is along Szentistván Street. It's quite straight and almost west-east direction. And the container is almost next to the street, so it's about 10 meters from there. So what we are interested next to air pollution is how it's connected to traffic. Here we manage the manual traffic counting with different kind of the vehicles. Here were acoustic categories. These are cars. Predominantly we have cars, so we can sum them all. And we can put together the traffic data with container data, and the golden one is our field measurement data. So they are quite synchronized. So we have the morning traffic peak here. So finally, I would like to summarize the results. So we find that Mathematica is a useful tool to visualize data, as you could see. But we had some troubles with huge Excel files, so it is not so convenient to work with Excel files. It's better to make some modification in Excel before I import my huge files in it. And as I see other talks, there are some nice changes in Mathematica 10, so we are looking forward to see the new version, so I hope it will be much easier then. And in respect to the field research, we are planning another measurements also. And we still not have the application to the model, so we have to compare field measurement and the model results, and model results should be closer and closer to our field measurements. See, thank you very much for your attention.